Hello, my name is Avery Hutchinson, and this is my report for the Oscillations lab. The purpose of this lab was threefold. First, we used observations of the motion of a system to determine the properties of the components acting in that system. For example, period of oscillation was used to find spring stiffness. We also used measurements about a system and knowledge of the system properties and interactions to build a model of the motion. And finally, we studied spring force and oscillations. Here is the video that my experiment was based off of. There were a few key outcomes of this lab. Firstly, we have our measured and calculated initial system conditions. The ball mass was given to be 0.402 kilograms. The ball's initial position was measured to be 0.108, negative 0.773, 0 meters, and the ball was considered to have started from rest. Calculation-wise, the spring stiffness was found to be 6.26 newtons per meter, and the relaxed length of the spring was considered to be 0.072 meters. The total energy of the system was constant, while the other three types of energy in the system, kinetic, gravitational, and spring potential, oscillated, with potential energy showing a greater amplitude than kinetic energy. The x component of the model matched well with the data, while the y component differed in vertical shift and amplitude. The main physics of the lab included using the net force acting on an object to calculate the motion of the object. The two forces present were spring force and the force of gravity. To determine the stiffness of the spring, I used the average period of oscillation between the x and y direction to calculate spring stiffness. My system was the ball, spring, and earth, which means there were considered to be nothing in my surroundings. Models and assumptions. For one, I treated the ball and the considered massless spring as a point particle system to simplify calculations. Thus, there were no air resistance, rotation, etc. considered. I only used data once regular oscillations of the experiment had started to simplify calculations and remove error from the initial position where the experimenter was still moving the mass. I assumed that the object started completely at rest and that the x and y values exhibited the same period, as I needed this in order to calculate the spring stiffness. This is my code that calculated the force of gravity and the spring force based on the equations discussed earlier. I then added these to calculate the net force, which was used to update the position and velocity of the ball and the position and direction vector of the spring. This is my code that updated the energies and the energy changes of the system. As we can see, the total energy of the system remained constant, which was expected. The potential energy of the spring and the gravitational energy of the system oscillate with more amplitude than the kinetic energy of the system. The model matches the experimental data relatively well in the x direction, with the experiments showing a slightly lower minimum value and a slightly offset pattern related to time compared to the model. The model in the y direction overestimates the highest point reached by the ball in the experiment, but slightly underestimates the minimum, and the period of oscillation, while offset, is the same for both models. The model does not match the experiment in terms of initial value of the curve either. There were many errors possibly present in this lab. Considering that the spring was massless, impacts the force of gravity that seemingly acts on the system, which could cause for a greater downward force. This may explain the shifted upward nature of the y direction model. Additionally, the experimental period of the x and y directions was not the same, and the model is based on an average of the two. This may have come from an imperfect selection of the center of mass in the tracker program. No forces external to the system containing the earth, spring, and ball were considered, which would ignore forces such as drag, which would change the overall motion of the ball. Additionally, no relative energies such as rotation or vibration were considered in this experiment, which may make the displayed values of energy not tell the full picture of the extended system. My model did follow the energy principle, though. Considering that my system had no net external forces acting on it, there was no work done on the system, and thus the total energy of the system should not have changed. Since the change in Total energy of the system was constantly zero. The model agrees with the expected result based on the energy principle. My average period in the x direction was 1.5 seconds roughly, while the average period in the y direction was 1.6 seconds. The period in the y direction was greater. This is probably because the ball was also experiencing the force of gravity in the y direction, which would have caused greater downward movement before moving upwards again, which would increase the period of motion. Thank you.